Hello, everybody. I'm Moises Hinojosa. On behalf of our Dean, Professor Arnulfo Treviño Cubero, please be welcome to our seminar of internationalization at FIME. This is a forum aimed at bringing the international world of engineering to our FIME community. In this webinar, we have great participants, and we will be happy to answer your questions at the end of the presentation of this day. It is really an enormous pleasure for me to introduce our speaker, my friend Carlos Esparza. Let me talk about a little about Carlos. Carlos will talk about accelerated product development with simulation tools, and he knows a lot about this subject. He earned the degrees of bachelor in mechanical and electrical engineering at our school, and he also studied a master's and a PhD in materials engineering at our Facultad de Ingeniería Mecánica y Eléctrica of this Universidad Autónoma de Nuevo León. He is an executive director with 28 years of experience in design and modeling technologies, team leadership, project management, innovation, product and tooling design, customer relationship management, new product development, and advanced casting developments. He has worked in a number of companies. He spent 17 years in NIMAC, Navistar, 2 years, and presently, he works at a company that is called Lesur Incorporated for the last 8 years. He managed also to be a part-time professor, both at our university and also at UDEM. He also has directed thesis. He has worked as thesis advisor for a number of students. And he is, and we are very proud that one of our alumni is doing this. He's part of the Industrial Advisory Board at an important university, the Mankato University at Minnesota. He's currently Director of Engineering and Quality at this company, Lesur Incorporated. He's happily married, and he lives in the US for the last 10 years with his wife and his 3 children. I want to add also that it is possible to combine different aspects of engineering and science, because Carlos is also a member of our Mexican research system. He's currently at level 1, and he has the potential to go higher in our Sistema Nacional de Investigadores. Welcome, Carlos.
Gracias, Moises. Thank you very much for your invitation, and I really appreciate this time to get back to my alma mater. I graduated in 2003 after 5 years doing my PhD. Married in 1998, then it was married in 2000, but I started the PhD in 1998. Then it took me 3 years, and the help of my family, particularly my wife at that time, to encourage me to continue and pursue my PhD. And then I completed when I was still a full-time employee at NIMAC as a head of the department at that time. I would like to start the presentation this afternoon, and welcome to everybody that is joining us today, this afternoon, from different parts of Mexico and United States, or maybe other countries. And I know this will be recorded and will be transmitted in YouTube and Facebook Live. Thank you very much if you watch it live or if you watch it record. Thank you. I please consider, you see my name on the screen. I have my account in LinkedIn. You can look for me very easy over there. You can connect with me, follow me, I will follow you. And keep in mind that I will try to do my best to summarize for what I learned maybe for the last 25 years or more. And maybe you will have more questions that it will be maybe impossible to answer all of those today. But keep in mind, you can reach back to me anytime. I will try to get no more than 40 minutes in order to keep you time for each of you or the people, the audience that would like to ask any questions. I would like then to move to the next slides. Moises already talked about my profile. I also like to introduce and have a profile overview of Lesur Incorporated. And also I would like to discuss the Lesur product launch system. But at the same time, I will say that other aspects of my experience before joining Lesur, etc., it will be covered during this event. Well, this is me, a younger Carlos in 2008, representing NIMAC as a keynote speaker in Berlin, presenting all the simulations capabilities that NIMAC had at that time. And it was a wonderful experience. I was really thrilled to receive this invitation from Dr. Flender and Dr. Storm from Magma, Germany. It was, for me, a great success on my career. And I say this is 2008. Yes, I joined to work with NIMA in 1994. It took a lot of years. And when I learned about Magma, and you will learn more about that in a moment, about this software, I was thinking, I think it was the year 1994 or 1995. I say, I want to combine for what I have just learned about my master's degree in materials engineering with simulations. And I would like to be at least I would like to be the best simulation engineer with Magma in the world. Okay, well, maybe it was very pretentious at that time, but in 2008, when I was invited to be a keynote speaker, it was really something that I liked a lot, and I continue enjoying until right now, even if I don't work directly with the software or other softwares that because I have been working with very good, talented engineers at NIMAC, Navistar, and also right now with Lesur, talented engineers that work very good with these tools, and you will discover more in a moment. Well, Lesur Incorporated is located in Minnesota. It's a half-hour drive from the airport, Minneapolis airport, or an hour, half-hour drive from Mankato, Minnesota, where is located the Mankato State, Minnesota State University at Mankato. This is a picture of the company. You can see in this area the foundry with different processes, permanent mold, sand, die cast. We have our machining division over here, and we have also our plastics division over here. Plastics division, you can see in this new picture, is here. I am responsible for the engineering of both the aluminum and the plastics, and also the quality for both divisions. You can see here at the beautiful Minnesota and the Minnesota River going upstream. It's a fun fact. How is this river going to the north and not to the south? Typically, it would be the case, but it will connect together with the Mississippi River, and then it will be named Mississippi River when they connect in the area of St. Paul and the Twin Cities. Lesur Incorporated is an independent total service custom producer of molded products in aluminum and plastic. It was established in 1946. It is a third generation privately held business and is financially strong, no debt, medium-sized company, and with a lot of different diversification. We work with permanent mold, die cast, sand casting, plastic injection, and we do also machining. We specialize in very complex castings. If we need to quote a project that is too simple, we will pass. We will tell our potential customer that maybe we are not the best fit for them, because we will prefer those challenges, castings like the ones that you see here, or plastic parts like the ones that you see here in these pictures. Some of our customers also diversify different industries, different areas, defense and industrial, agricultural, etc. You name it. What is our Leisure product launch system? Well, I would like to start first that this was influenced by, at least for me, when I was working at NIMAC, I was influenced by Dr. Stefan Tonke. He came from Harvard to work with NIMAC, and we developed a product launch system at NIMAC. I was just part of one of the milestones, we call it milestones, and we ended with a very good product launch system with 11 milestones. It was a great system. He teach me a lot, Dr. Tonke, and we learned a lot at NIMAC. We learn about the concepts of front loading. You read these two books, in particular this one from, I think is from 2000. And this new one, I read this book lately. I love this one for manufacturing. This is more for for software development. Sorry. Sorry for that. Yes, this second book is developed in this new area of software development, and he talks about different examples with Google and other companies. Over here, he mentions all of his experience working with Toyota, BMW, Ford, and other companies, and he found interesting facts. The Japanese companies didn't have the best software that, like, compared to the American manufacturers. Yes, the American manufacturers had better tools for simulation and CAD versus the Japanese. But the Japanese, in this case Toyota, were able to use this limited software to a perfect efficiency. It was great what they can do, and they were able to reduce the product development time in 2 years versus the typical 5-year development. It will take only 3 years. And with, as I said, not the best tools maybe in the market at that time. It was a perfect example of how to use the simulation tools. I think you will enjoy, if some of you would like to learn about more, yeah, this is a very good book. Well, something that you can maybe learn, this is another source. You will see that the traditional design process is this one here. We can see these are maybe the milestones for any project progress. Then typically you will start and less effort is required at the beginning. More effort is required at the end, and then less effort at the end to finish the project. But what Dr. Stephen Tonke and others were saying and promoting was the preferred design process. This one here, number 4, more effort upfront, more resources, more discussions, more inputs from manufacturing, etc. A lot of front loading concepts. That's the what he called it, front loading concept. Okay, then yes, it's cheaper to do changes in the computer, doing a lot of simulation work here versus making changes on the tooling over here. It will be very costly. Okay, this is Leisure product launch system, very simple scheme, basically to mention that we develop a 7-gate system. By the time I arrived to Leisure in 2014, they had already this system in place. I was just trying to incorporate some of the activities or achievables and accountability that was required, and in particular introducing the use of more simulation, in this case MagmaSoft, and design up here, trying to for me it's very good if we can start a project over here and at least have 4 weeks for simulation. It will be the best. And then you will start the tooling build, and then you will have a sampling process, and hopefully with less iterations, then you will be able to submit your PPAP. Another influence that I had was from Dr. Steven Eppinger, professor from the MIT. I attended one seminar for a week over there, not only with him, but other doctors And I learned a lot during that. And this is just one of the books that I read. And when I returned years later, I was teaching this course and using this book, the previous versions, in the Universidad de Monterrey. I was a teacher for the class of product development for both the bachelor and master degree over there. I also obviously work with the students, and I invited them to work with me at NIMAC as internships, and some of them stay there. Some of them went to other companies, like in Sweden, for example, and they finish a master degree over there. Yeah, it's just an example of people that very successful. You will find in internet very easy using this title, for example, and you will find something like this that he will describe. Dr. Eppinger describes, obviously in the book, but if you don't have the book and you can just browse the internet, you will find something like this, that typical traditional stage product development process include the planning, then the concept design, and then the system level design, detailed design, integration test, release. And then you will have some milestones, reviews, or gates over here. Yes, sometimes you can get back if needed for iterations on Planet, but sometimes in certain levels, you can also introduce a lot of iterations over here if needed. That's similar to some of the concepts that Dr. Tomke from Harvard was teaching me. This is another of multiple PDP, product development system, that you can find in this book. As I said, this is just another example, but this is more for software development. You start here, and then you pass for a planning phase, and then you move into concept design, and then you move into system level design, then detail, integration, test, and then after you pass this, you continue again, planning, and et cetera, et cetera. Yeah, this is also very similar to the Agile, the new software development strategy that is being used for the last maybe 20 years. The Agile development is something like this, right? With the sprints and all of that. We can talk about that if needed. Well, Lesueur. Okay, this is the product launch system at Lesueur. We have 7 gates, as mentioned before. We have our coding process, and then we have the product development process, and then we will have a tooling development process. And in parallel, if we are doing the machining in-house, we will develop the machining, or we partner with our customers, they will be doing the machining sometimes. We will intend to start the personal development people that will work on the floor, the operators, and try to be ready for the time at gate 5, as you can see here, is the pre-sample meeting, and then we will have a lot of iterations over here, and then eventually we will reach gate 6, we will submit our PPAP. PPAP is what is needed to receive approval from the customer. Some of our customers require only something called a first article, and then we move into production. Well, over here, maybe, sorry, it's a very small picture over here, but you can see that between gate 1 and gate 2, we did some designs, and we were saying, okay, yeah, we can do a 2-cavity tool, but what else if we can maybe try to accommodate 4 cavities versus, or 4 parts for the tool versus only 2. And then we simulated that different, and then we evolutionated, and we made a better refined decating design system. Decating is something here that will bring, in this case, we are talking about aluminum cast, it's in die cast. Aluminum, the molten aluminum will flow through this gating system and then will form yes, if everybody's in agreement, then we will have this gate 3 final tooling design review over here, and then we will move into the tooling construction, and then the tooling will be back, and this is a picture of that tooling. Again, sorry, the picture is not the best, but then you will see that it's very similar to this. You can see it here in the final product, very similar to what we designed over here. Yeah. Well, another way of seeing this process in a very summarized view, we have obviously a very detailed concept, like also NIMA has a very, very detailed concept with roles and responsibilities from different departments and people looking for accountability from different players. And you can see here the attendees that will be in the meeting, who is the person calling for the meeting at the first time, then the cost estimator before the gate one meeting tell me, hey, Carlos, director of engineering, okay, I'm responsible to define and say, well, who will be the project engineer? And then the project engineer he will be in charge of the project. You can see here, he is the owner of the project. We would love to have a project engineer in charge until we get into production. Yes, we want to have all the inputs from process engineering and manufacturing over here to collect all, as I said, the front loading over here, and then run a lot of simulations and finalize our tool and review our model flow analysis in order that we can confirm, yes, this is exactly what we want for the tooling. This is then the typical design, the build of the tooling, and then the test. Yes, that's the traditional one. But if we introduce those other concepts of front loading and what Dr. Tomke teach is something like this. What he said is you need to do more design, build, and test. But you say, well, build, if you are building the tooling here, what's going on? Yes, you cannot build a tooling here. Well, yes, you can build a tooling in the computer, for example. You can build a tooling in drawing, for example, and then you can at least test it. Is maybe you use paper, maybe it's just computer, maybe it's just design. Maybe you don't have a software like we have right now with Magma, but it's still, maybe you hire and you outsource those tests. And then you design again, and then you build, and then you test again, and the same. Or sometimes you will have time to do even prototypes, and then you will print, for example, cores, sand cores. Again, if you have the capabilities in-house, great. If not, you can outsource those, and then you will prototype more. And then Stefan Tomke collect these low fidelity prototypes. Okay, the simulation models, the 3D printed models, plastics, even if it's an aluminum part, but it's a prototype, it's still a low fidelity prototype. Because the high fidelity prototypes will be the ones that you will build here, okay? When you already have your tooling, your production tooling, that's your high fidelity prototype. And then you will test it, the physical part over here. And that's exactly what you intend, is to avoid most of the trial and errors over here and try to do most of the trial and error over here. I think this is the main message for you, for all the attendees to this presentation for today. I will spend and make examples to you, but again, this is the main message. You start at gate one, but then how you cross the cliff, how you will go to the gate 7. Well, the only way to do it is to teamwork, synergy. It's not only the project engineer. It is not only the quality engineer or the process engineer or the operations manager. It's a teamwork. And as you can see here, you don't have a bridge, but the bridge is the people and the learning, okay, of the people, and all the work that they do together in order to get agreements together, okay. Well, if you need a simulation software, what you will ask for that? I will obviously talk about foundry here. I will talk about aluminum, but this can be also applicable to plastics, for example, or can be applicable to steel or forging, or I don't know, even designing a new hydraulic system in a city. Well, okay, you can simulate all of that. You can simulate the filling of plastic. You can simulate how is the dam being filled with water. You can simulate even a nuclear bomb, for example. But all of that, if you want to really capture what is you try to capture the reality, how you will do that? Well, most of you will say, yeah, maybe with physics, with mathematics equation, right? Yes, you are an engineer or a scientist. Yes, you are correct. And then you will say, first you will need to understand what's like here on the picture, okay? We have different concepts in principle. Those are natural principles, okay? This is the pouring cup. You have a potential energy in this, and this potential energy will transform in kinetic energy. During the kinetic energy transformation, you will have friction loss, you will have also velocity and temperature and pressure force. For us, on the casting world, this is critical. You need to really understand what's going on, what's here, okay? What is here? What kind of alloy is here? Aluminum alloy, okay, what is that? How you capture the phenomena, okay? Well, that is captured with all of these equations. And then you will say, oh, what's going on? How you jump from this physical and metallurgical phenomenon and go to some theoretical description that you can see here, and then you will have some numerical analysis, then you will have results, etc. And then you are a person that doesn't know anything about differential equations, and in this case, partial differential equations, you will say, I don't understand, Carlos, what you are presenting here, okay? Let me try to explain. As I said, there are principles. And those principles, like the mass conservation law, is something that was discovered by Newton or other theoretical genius in the history. And the momentum of conservation law, or the energy of conservation, all of those equations that you can see here includes the velocity, in this case, in the X or the Y or the C, we live in a three-dimensional world, okay? Yeah, X, Y, Z. And you also have, later on, for this movement conservation equation, you will have also gravity, and you will have pressure, and you will have viscosity, okay? The viscosity of the aluminum in this case, for example. And time, okay? We didn't have time here, but now we have time here. Density, okay? And yes, this equation is only for X, and this equation is only for Y, and this equation is only for Z. And then you have an energy conservation equation. And you have, again, density, capacity, the heat capacity is different. The heat capacity for a sand core is different for a steel mold, is different, obviously, for an aluminum, etc. Temperature, time, again, you repeat the same. K, what is K? Well, K is the conductivity of the material. What is S? The entropy of the heat that you will lose. But then you say, okay, well, but Carlos, what I will do with all of this? Well, you need a software, okay? That's the reason to consider the simulation software. Well, but there was a problem. Only having these equations and all of these variables, something was missing. And it was in the 60s that Dr. here developed the VOF method, okay? Yes, some of these equations are 200-year-old, 100-year-old maybe. This method is from the 60s, developed in the United States by this person, Dr. Tony Hirt. He was previously a scientist on the Los Alamos National Laboratory. He was the founder of flow science, okay? I worked with him. I went to flow science many years ago. I met him, and I was doing my PhD at that time. And I even asked him for the original, or one of the original copies of his publication when he discovered this method. And I learned a lot from him. He is a very great person, okay? Then Flow Science developed Flow 3D. I used Flow 3D during my I also use Magma, and I also use other softwares like Abacus and ANSYS, working with NIMAC and Arena Flow, etc., etc. But yeah, these methods help the developers, not only Flow Science, but Magma and other companies together to develop a better feeling, or we are in this case, we are talking about feeling the velocities. Okay, this is a fraction of a cell that is with a discretization. Another person that influenced my career, Dr. Diran Aprilian. He's working right now in University of California in Irvine, and I met him when I was working at NIMAC and working with him and other researchers when he was part of the Worcester Polytechnic Institute and the MPI and other resources. I learned a lot from him. I attended a seminar in one of the summers, maybe 20 years ago, for advanced casting development at WPI. And Dr. John Campbell was there, and I met him. And also Dr. John Campbell was hired by NIMAC, and he's an author for many books. I'm just placing here two of the books, pictures, for very famous books for this guru. And he developed the coursework process. Okay, this coursework process was it was acquired by NIMAC in certain moment for the Canada plants, and as I said, he continues to work in foundries around the world. I worked with him in some projects, and it was wonderful experience. This is what he did. Okay, he was a professor in Birmingham, in UK, and then you can see here that he developed together with other people, as you can see in this reference. You can find this on different publications, Cyril, Holiday, and Campbell. Well, this is aluminum being filmed with X-rays, okay, with an X-ray machine, and this is something that happened in the 90s, okay? And at that time, obviously, the computers were not too powerful like right now, or the software not even were too powerful at that moment. And then they created this mold in sand, and they said they decided to film in X-ray, and then capture, and then they invited all the companies, Magma, Flow 3D, and other players. Okay, all of you came and simulate this. This is the geometry. This is exactly, etc. Then yeah, I did this, and then they published results, not only the video but also pictures like this, and then they conclude that what they were seeing in the pictures after the X-rays was something like this. They say, well, this is a turbulent flow. This is the behavior versus these other two potentials. Again, if you remember, the phenomenal can be described by the mathematical equations, and you can simulate something like this or this, if it is a viscous laminar flow or a low viscosity laminar flow. In this case, what they created was something called a turbulent flow, okay, because they pick a higher, in this case, a foot, 3.5 centimeters to pour the metal. Well, as soon as the aluminum starts hitting more than an inch, it will have a highest speed. Okay, it will hit down here after 1 feet, more than 2 meters per second, the velocity, and it will create the splash that you saw in the video or here on the pictures. Dr. Flender, he is another person that influenced my career. He is the founder of MagmaSoft, SigmaSoft, and he's also the owner of Dr. Flender Holdings, and they acquired Flow Science this year. They also have Flow 3D as part of the holdings in this company. Great person. I work with him, and I learn about a lot from Magma and his team when I visit Aachen in Germany some years ago. This is a video of a work they made at Lesur by Ethan Climbs and Carlos Esparza. But this is the same, something what I did when I was doing my PhD. And as you can see here, is very similar to what what the video that you saw from Dr. Campbell, a very good representation of what was going on over there. You can see here pictures of that. You can see this kind of behavior, for example, or this hole over here. Well, over here you have air entrapment. It's also here. The air entrapment will be a problem if this is our casting and we call it this gaining system. Yeah, this air entrapment or this air will bring problems, okay? Problems, defects. Then, yeah, you can, with the software versus use the X-rays, you can see air entrapment over here, the turbulence, the air currents, or the high speed that we were talking. Dr. Campbell talks about that. You are above more than 0.5 meters per second, you are in a problem, okay? You will have a turbulence, and then you will create oxides, potential problems, big films, and other things that he discussed in his books. MagmaSoft, they are capable right now. I took this picture from the internet, from their websites and brochures that they have. The software is very powerful. In my opinion, it's the best software in the market for the foundry process simulation for multiple processes. In this case, it's permanent mold. You see here in blue, the steel mold and some sand cores, etc. Yes, a very detailed that you can run right now. And you run this in a desktop computer. Well, over there in 1994, when I started, yes, you were able to run that kind of simulation. The models didn't exist at that time, for sure. The software was able to run only with one processor. Took years for them to develop 2 processors, okay? The capability to work. Well, yeah, right now you can use 32 processors or 64 processors in a desktop computer. Yeah, very expensive, powerful computer. But comparing to what you can have in the year 2000, for example, that is totally different. Yes, the PC cluster technology that NIMAC acquired at that time, we were the first in America, or at least the first in Mexico. I was told that we were the first in America, maybe after 4 only, to have a PC cluster technology. We were pioneers on that. We partnered together with Magma when they were still developing from moving to use CPUs to start using 4 or 8. We needed a PC cluster technology. And all of this works with Unix or Linux, never with Windows at that time. Yes, not right now, as I mentioned, you have all of those capabilities with Windows, okay? But other examples, you can simulate and check temperature, or how is the metal flowing, or how is the air contact, or how is the metal age. The metal age is something important. The first material that enters into the mold by time, or the last. Well, the first is the one that has the most damage, for example, that will produce the more oxides. Well, you want that to be away in an overflow, for example, in the case of die cast, or in a riser in the case of permanent mold. You can predict microstructure and mechanical properties with Magma. Right now, you are able even to predict the heat treatment, the quenching, and even the trimming. And you can even check the distortions and simulate the straightening. All of that is capable with the software. They have evolved a lot with a lot of capabilities. Again, comparing to what we were able to do 20 years ago, well, it has been evolved a lot. They also develop core simulation, the sand core in this case. You can simulate how you are making a core. You can predict right now different kind of problems with the sand core, gas distortion, or sometimes the evolution of gas. If it's an organic binder. Flow3D, well, it's another software that you can consider. It's a very powerful software. As I mentioned to you, I also used this during my PhD studies. With this software, you can simulate the hydro, for example, a river, a dam, welding, the aided manufacturing process. All of these, the casting simulation, all of these can be simulated. And again, I'm mentioning two softwares. There are more on the market. This is just a picture of take it from the University of Wisconsin-Madison. But this, you can check on this website, or there are multiple websites. I just mentioned here for me, for other kind of analysis, you can use ANSYS, Abacus, Nastra, and you can use OptiTrust or other softwares. Now I have an example, okay? I think some of you will say, well, Carlos, but you sound more like a theoretical professor. We need examples, real examples. Okay, yeah. These are examples. They are developments of a lower oil pan, okay? And yes, we follow this kind of methodology here. We run first simulations. I need to say that Ethan Climbs is the person that did all of this work. I'm presenting what he did. Obviously, we coordinate together. And then he starts with an original orientation. And then sometimes we would like to flip over the orientation of the casting. And then we will do the filling and solidification, conceptual design. And then we run, and we start to introduce the first gaining system. And then we run iteration. And then we will flip over if needed, okay? And then we refine the gating if needed, and we do more iteration. And we can even check what if scenario. We can do, starting to do some kind of optimization, okay? We can introduce later on cooling lines if needed, okay? Process parameters, iteration. Finally, or later on, you will start using the tooling models, because at this time, maybe your tooling is still being designed. You are still iterating, making a lot of iterations. Well, obviously, over here, you are already introducing the tooling models from your CAD software, Unigraphics, CATIA, SolidWorks, Creo, etc., etc. Process parameters are being introduced. The variation in process parameters, okay, are tested. This is just a quick picture for this oil pan. Yeah, as I said, version 1 in this orientation, version 2, the casting is oriented. Yeah, over here, as you can see, we didn't have any casting tooling model, just the casting. Then we start to introduce how will be the gaining system. Okay, we have version 3, 4, etc. We have risers. We introduce now a pouring cup over here. Then now we have a better definition over here. Okay, yeah, version 16. Well, imagine version 16, okay, and you try to do all of this in 4 weeks. It's a lot of work, okay? But this is what you intend, to have the best possible casting and have the best prediction of the effects, okay? And then the first sample. And then we had this, after 17 simulations or 16 simulations, we had the production of first part. Yes, version 1, version 2, we predicted defects like this. These are porosity shrinkage. This is the tooling models. Okay, as you can see, this is version 16, very good defined. This is a video that I will play. I hope you can see this video live, and you can see how is the filling and the rotation. This is a tilt process in permanent mold. And then how the solidification is taking place, okay? The aluminum that is being poured at high temperature, and then it will start to solidify. And then you are looking for a directional solidification. Then the center of this will start to solidify. In some areas remain, the material that is disappearing from the screen is solid, okay? It's solid, it's below a certain temperature, and then it's solid. But if something like the blue area that you saw over there, isolated, that could bring maybe problems, okay? This is another example, another video. In this case, we call it fraction solid. Okay, it's very similar to what you saw before. Pictures, and then this is the prediction of porosity. A very clean casting. Yes, with some specs like here or here or here or here. Okay, then this is the tooling, and this is a picture taken on April 10. Okay, this project started in January. Okay, the tooling is here in April. Okay, and it started to be sample for the first time, and this is one of the first castings produced. And then we inspected, we did an X-ray inspection, and you can see here very clean casting. Okay, the walls, okay? Yes, some kind of defect over here. Another defect over here, okay? If I return back to some slide, you will see that this was predicted, or the other one that was also predicted. Although this was maybe our main problem when we were developing this part here, other X-rays. But at the same time, we were developing a more challenging project, okay? The mid-pan. Then it was not only the lower all pan. The mid-pan is a different kind of project, okay? It required more attention, but it's only the same resources. It's the same engineer, the same designers, the same project engineer, the same process engineer. At the same time, okay? You try to get, yes, you follow the same concepts as mentioned before. Yes, we simulated without any gating system and riser. And then we try different concepts. And when we tested the first 4 concepts, we had all of these predictions for the shrinkage. And then we needed to decide what will be the one that we would prefer, okay? Because the 4 of these on the screen has different risers, or mazarotas in español, risers, feeders that will bring metal. Well, I needed to pick a decision, and I picked one, okay? Then we pick one, and then after checking all of the, yes, this is just you can follow what Ethan was putting on his log, okay, with the input from Mark, the project engineer, okay, the different systems that is being tested. Yeah, we tested these concepts, as you can see here, and then we picked one. This one, okay? The version 3, then after version 3, we will develop the rest. Version 3 is our master, and then we will go, and then we will, version 19, and then sorry, I need to play the video. Same process, tilting, same kind of video information with temperature. Okay, as you can see there. Prediction of defects, porosity. And this is a picture of the tooling on the floor. One of the first castings made. Shrinkage in one area, very clean in this area. Another defect in another area. This is the product launch system that we have. And this is the application. Okay. Yeah, this is the application. You can just follow in YouTube or check this website to see. Other project that we are working right now with BRP, they are developing something called COST, a new engine that is not presented over here, is just down here. I cannot show you the castings. Yes, we have castings already. Yes, we have simulation, but I cannot show you. Sorry. I have some acknowledgement, and I think I didn't took care of the time. I went over the 40 minutes that I was thinking, but anyway, acknowledge for the people in my career, other people, nice professors, nice friends, colleagues, and family members. Professors from Dr. Valtierra, Dr. Colás, Dr. Moisés Hinojosa, José Jesús, and Moisés Talamante Silva. Special recognition to one of my students, okay? I think Damián Amaya was one of the students that he was my student in master degree in the Universidad de Monterrey, and he was also, I was an advisor for his thesis. And he always called me maestro, but I think I learned a lot from him. He was my student, but I think he's also my maestro. Thank you, Damián. Finally, I would like to say, well, I'm very happy with my family. My kids are, Carolina is finishing in 3 years a bachelor's degree. Maria Jose is already accepted by the University of Minnesota and California Polytechnic Institute. She's still waiting for other schools, and then she will decide. She plans to do the industrial engineer in 4 years, bachelor and master degree in 4 years. Carlos, my son, is 1 year younger, and he's planning maybe to be an aerospace engineer or a physician or sorry, physics, or maybe a priest, or we don't know, but he's very talented and he has a GPA of 3.8 or 3.9, and my wife, Maria, without her, for me, these are my accelerated product development, okay, my kids. Lesur, okay, we want to be a supplier of choice, the employer of choice. Right now we are hiring. Okay, someone is thinking about a career. This was 1 hour ago in LinkedIn was published, up to $90,000 for a network administrator. And this is, I think, this last slide. I think this is me, Carlos, and Lesur believe in me. Okay, Dick Seidenstreicher, my boss, president of Lesur. He gave me the opportunity 8 years ago to be the director of the engineering and quality later on. And I thank you for them. I'm finished. Sorry, Moises.
Great. Thank you, Carlos. Please receive our first virtual round of applause for your really wonderful presentation, Carlos.
Thank you.
I wonder if you can see the Q&A section.
Yeah, I see 4 people presenting. I will need to use my reading glasses.
Okay, you have some comments from Eduardo Solis. Maybe you can read them.
Yes, of course. Eduardo Solis is a very good friend that I worked with him in the past. I pleasure to see you and attend your presentation. Congratulations for your solid career. I captured 2 things. But then okay, I think then first thing, driving companies like NIMA with a strong international presence have incorporated academia to enrich their process. So cooperation between companies and academia pay back. Of course, it's no-brainer. In any place in the world, in the United States, in Mexico, whatever. There are great design centers in Mexico that apply tools for complete simulations like Schneider Electric, yes, Monterrey, NIMA, of course, GE, Aerospace in Querétaro, Honeywell, yes, Mexicali. So for young engineers, a career that includes the ability to perform simulations is in need in Mexico. Of course, yes, I completely agree. I think there is a lot of potential for these kind of careers for simulation. As I said, I'm just talking about foundry in this case, but there is a lot of potential. The computer capabilities, the software is endless opportunities over there.
Great. I'm inviting everybody to send your questions to Carlos at this moment. You can use the Q&A tool. And meanwhile, I want to ask your comment, Carlos, about this current, let's say, first with this term digital twin. What can you tell our community, our students in particular, about this digital twins thing?
Well, I didn't mention anything about that, but I know about the concept. I know that the digital twins is something being developed lately for the foundry 4.0 or in general industry 4.0. Is like the Internet of Things. Okay, how to predict better the flow on the manufacturing place. And connect all the equipments to your manufacturing system and then have real data, okay? For example, if you have an advanced MES system, with that advanced MES system, you will be able to have live information for quality, SPC, for example, and other aspects of the business. Again, I'm not too close. I read about those concepts. I need to learn more about that.
Oh, you know a lot, but it's maybe just that it is very new, the concept. But it's exactly what you do, a virtual thing that responds to the reality.
Right, and I think I maybe didn't mention this, but one of the reasons to use Magmasoft, in my opinion, is because you are not only simulating the product, okay, the casting, making of one part only. No, you are simulating the tooling, you are simulating the machine you want. You can simulate more process, as I said. You can simulate since the raw material to even heat treatment or trimming or machining. Yeah, then there are software that are capable. Or you need to integrate, and then the results from Magma then can be sent to Abacus. Okay, we did that with GM and Ford in 2008, I will say, and they continued the structural analysis. But it was different, obviously, for them receiving the results from the casting, and versus just thinking that the casting is perfect. No, it's not perfect. Then those defects that Magma predicted now are being used by these other software like Abacus and ANSYS, etc. And then GM or Ford were able to advance from there.
Great, great. You have another question from Jose Luis Garcia Lozano. Thanks, Jose Luis. The question is all engineering developed at home, or do you use engineering service providers?
We try to do most of that at home. Sometimes we don't have capabilities for some of the, for example, heat treatment is something that we cannot simulate in-house. If we need, we can try, or for example, the stress analysis is something that we need to hire services outside to do that. It's possible.
Okay. Well, this is for the moment the last question in the Q&A section, but I want to ask you, Carlos, what piece of advice can you give to our let's say a student that is beginning his program studies or is about to graduate? What will be your best piece of advice for a young engineer to be successful internationally?
Oh, okay, of course. Yes, well, obviously, learn English is important. Okay, you need to be a master in English. It's not easy for a Spanish speaker. Maybe for few people like Jose Talamantes, my brother, he didn't study and he was a master in English. But yeah, the technical skill is something that you will learn in the school. And then you need to pick your career very careful for what you want. Okay, you want really to be an industrial engineer or a chemical engineer or any other. Well, pick the best that you think, depending on your desires. Okay, but the technical skills are hard skills. We call it hard skills. The soft skills, the people, the emotional intelligence are more important than the hard skills, okay? Then, yes, you need also to learn about emotional intelligence. It's something that maybe is not being taught. I don't know if lately FIME includes that kind of information, but it's something that at the end, the preparation in each of you bachelor that you will pick gives you some tools and skills, and then you have the mindset that you will continue learning the entire career in your life. You will have a learning experience for your life. If that's what you are thinking, yeah, you are in the correct path. If you are thinking that, I just want the paper and put it on my wall over here with a bachelor or a PhD, well, maybe you are wrong.
Great. That was a great piece of advice, Carlos. Finally, what would be your suggestion to a young student that is in his first year? What kind of software, for example, or programming can you suggest to begin to build a strong, let's say, equipment to be successful in the engineering world?
Mm-hmm. Perfect. Yes, I think lately most of the companies, for example, the slide that you saw that I presented from the University of Wisconsin-Madison, all of that software is available there to use a lot. It's for them, for the students. Yeah, I think I will recommend maybe if you are in the mechanical engineering field, obviously learning a software like SolidWorks, Creo, CATIA, etc. to design is something that you need to start with. And that's the foundation. And then if you want to go into industrial engineering, yeah, you use those models that you create, and then you can simulate the entire factory, okay, 2D or 3D, and then you do your value stream mapping, for example, in the computer. Or you pick another field and then you want to be a CFD analyst, okay, the computational fluid dynamics, similar to what we presented today. Yeah, well, in that case, yes, you will need maybe Magmasoft, or you will need Flow3D, etc. But maybe you would like to optimize the structures, okay? Maybe you would like to work with the new company of the future that will have the, not the cars, but the planes, electric planes. And then you need to reduce the weight. Okay, well, there is optimization software for that, Optrus and other software for that. Then anyway, I think there is a lot of avenues, and sometimes you can combine and it's like another tool, okay? You are a chemical engineer, for example, well, you can learn about digital products, softwares, because even if you are used in the petrochemical or battery design with lithium, etc., well, you can use some kind of softwares as a tool, okay?
Great, great. Well, it was really a wonderful presentation, Carlos. We thank you very much on behalf of our Dean, Arnulfo Treviño, and all the FIME community. Please receive another virtual, very warm round of applause. Muchas felicidades, Carlos. Mil gracias.
Muchas gracias, Moises. Thank you very much to everybody in the community. And as I said, I'm there in the LinkedIn, in Facebook, and other accounts. But yeah, you can connect with me anytime.
Well, really, we're really happy and very thankful to you, Carlos. Please have a great weekend. And thanks to everybody. Thanks for your time, your patience. And please be connected. We will prepare more webinars like this. We hope it will be a difficult task for us to have such quality like this presentation by Carlos, but we will do our best to offer you this kind of webinars. Thank you again very much, Carlos. We will send you a good, nice diploma signed by our dean shortly. Thanks to everybody, and thanks for all the technical help that we received from the school. Thanks to Andres and all the people that is, let's say, behind cameras, backstage. Thanks to everybody.
Thank you. Thank you. Bye-bye.
Have a great day and great weekend. Thanks.
Bye.